Thank you, Danielle. You just made my life easier. Okay, now as Danielle showed, we often use external noise. And in all the examples that Danielle showed, when we use noise, we're actually interested in characterizing the processing in noiseless conditions. So noise is actually just a tool to help us characterize visual processing in noiseless conditions. Now, I'm going to show, I'm going to talk about the first paradigm I'm going to use is contrast sensitivity. And the idea of, well, here you have a gabor, you can measure the sensitivity to this gabor. Now, the ideal of what the observer, the model observer, the simplest form of the model observer, Danielle already talked a little bit about it. Well, first we know we have internal noise, and so this internal noise actually adds to the stimulus. And then, so we must do a calculation, so we have a signal that's embedded in noise, okay, even though the stimulus itself is noiseless. So the sensitivity will depend on two factors. You have the internal noise that is added, and you have the calculation efficiency, which is basically the ability to extract the signal from noise. Now we want to measure these two factors, and that's why we use noise. So we present a stimulus which is embedded in external noise, and we do this because when we do so, the internal noise is negligible, so it has no significant impact. So the performance only actually depends on the calculation efficiency. Now, what we assume when we use this type of model is that the calculation is the same. The same process operates to extract a signal embedded in external noise as a signal embedded in internal noise. And that's what we're going to criticize, or that's what we're going to test. Is it the same process that operates in these two conditions? Okay, so when we use noise, here's an example of a detection task. You fixate in the center, and you need to say the target appears to the left or to the right. So here the target flickers on the right side. So it's really just standard detection, and you can just ask subject, is something presented to the left or to the right? Now if we add noise, the stimulus can look like this. So you fix in the center, and you have noise that's added on both potential target locations. And so that's how noise is usually used. Most of the time, people add noise that turns on and off with the signal and is actually at both target locations. Now, when you do this task, my impression when I do the task is that this is not a detection task anymore. I know that technically it is a detection task, it is to say whether the signal is presented to the left or to the right. But when you do the task, if I ask you on which side is something presented, well, you're probably going to say, well, I have something presented on the left side and something presented on the right side. So the task is not actually to say, is something presented to the left or to the right, but on which side is that the object I perceive more similar to the target I'm looking for, here, vertical gradient. So that's what we're going to ask. We're going to ask, is this a detection or a recognition task in the way that the stimulus is actually being processed? Now again, the noise paradigm assumes that this would still be a detection task, and it assumes that the processing is not affected by the fact that we add external noise. How are we going to do this? We're going to use crowding. Okay, we know that crowding affects recognition, but it does not affect detection. So we're going to add some flankers that are either horizontal or vertical around the target. So now we know from the literature that these flankers are not going to have any impact on the detection threshold when there's no noise. Now we're interested in high noise to see if these flankers are going to have an impact. So here's the result. We have the crowding effect for both when there's no noise and when there is high noise. So a crowding effect of 1, that's a detection threshold ratio between when the flankers are horizontal versus vertical. And so a ratio of 1 means that you have exactly the same threshold independently of the flanker orientation. And as we see, when there's no noise, we have the same threshold. This is not new result. This already has been observed. Crowding does not affect detection. But in high noise, we get a huge crowding effect. Detection threshold are higher when the flankers have the same orientation as the target, that is vertical. So this suggests that this is a recognition task. This is processed as a recognition task and not as a detection task. So now we're wondering, okay, why is the processing strategy changing? Now, there must be something different between the internal noise, because here, obviously, I'm not claiming that we don't have any internal noise. Obviously, we do have internal noise, but there must be something different between the internal noise and the external noise that we are using. And one striking difference is that the noise is actually spatio-temporally localized to the target. So what we did, we used diffuse noise, and we test exactly the same thing. And our claim is that this is more like internal noise, which is broad and it's there on the screen all the time. And if you fixate here, and I ask you on which side is something presented, well, you probably have the impression that there's a target presenting on one side and there's nothing on the other side. So it probably feels more like a detection. So now we're going to apply the same paradigm to test whether this is detection or recognition. And so as a control, we just set with local noise again, we get a crowding effect, but with extended noise, we get no crowding effect, suggesting that this is a detection task. So we conclude that this, when we use extended noise, that does not trigger a change in processing strategy, but when we use localized noise, then it can trigger a change in processing strategy. Now I'm going to switch over to a completely different paradigm, but it's exactly the same idea about noise. Now it's voluntary averaging. Now, if I give you a stimulus, you have 4 gabors, you need to estimate the mean orientation of these gabors and say whether it's tilted clockwise or counterclockwise relative to vertical. Now, we have the same model observer. Now first, there's precision estimate, so you're going to have to estimate the orientation of each gabor, and your precision estimate is more or less accurate. So, this is your internal noise. This is a precision estimate of the orientation of each sample. So there's no pixel noise. So really here, the idea of internal noise is really the precision estimate of each gabor. Once after you do this, well, you're going to have gabor that are tilted at various orientation because of your internal noise, but you don't judge each orientation, each sample exactly the same way. And then you're going to have to average these orientations to make a judgment. And again, your sensitivity is going to depend on 2 factors: your precision estimate, which is roughly internal noise, and your ability to average across samples. Now, to measure these 2 factors, we can use exactly the same technique, and it's to add external noise, here external noise being an orientation jitter. So that when we do this, well, any small imprecision in the judgment of the orientation is going to be negligible. It's going to have no significant impact. So that when the threshold, orientation discrimination threshold, is going to depend mainly only on the averaging efficiency. And now again, what we're going to ask is that, is these 2 process exactly the same? The model assumes that it is. Now we're going to test this. Okay, so I'm going to make you do the task. And so we present you 4 gabors, and you need to say the tilted clockwise or counterclockwise relative to vertical. And when you do this, now this is voluntary averaging, and I want you to pay attention to the processing strategy that you're using. So here's an example. So you see the 4 gabors, and probably in your head, at least in my head, what's going on is I'm looking and I'm saying, okay, this one's pretty much vertical. I have 1 tilted to the left, you have 2 that are tilted to the right, and I can almost hear myself thinking and judging the orientation of these gabors, and then I make a decision. I'm like, okay, well, I'm going to guess that it's tilted on the right. So you can be conscious of this processing because this is voluntary averaging, so this is a high-level task. Now, I'm going to make you do the same thing. So if I ask you here to judge the mean orientation again, exactly the same task, except that I did not add any variance to the gabor. So that's the condition where there's no external noise. And I don't know for you, but for me, I don't have the feeling that I'm doing exactly the same task. I'm looking at these and I see them all as pretty much vertical. And so I'm not like judging one and saying, okay, well, it's slightly tilted to the left, the other one's to the right, and trying to average these. I'm just like looking at all these, and there's no like averaging that actually goes on in my mind. I'm just seeing them all as pretty much vertical. So now we're going to try to show this empirically, show that in this condition, we're not actually averaging. In this condition, obviously, we are. The way we did that is that we measured averaging efficiency when all the Gabors have the same orientation and when they differ in orientation. And we measured, to measure the efficiency, we measure with 1 Gabor versus with 4 Gabors. So you should be better with 4 Gabors than with 1, because here you have orientation jitter that is added to each sample. So it's like you take 4 measures of the same thing and you average out, you'll be more precise than if you take only 1 measurement. And here's the result that we get. When there's high noise, when there's a lot of variance across the board, the observer were better than when there was only 1 Gabor. So this is the averaging efficiency, so meaning that they are better with 4 samples than with 1. But when all Gabors have the same orientation, they have the same threshold whether they have 1 or 4 Gabors, shown here as the ratio, the averaging efficiency of 1. So, what we have here as a result, if I summarize everything, now if, when we study one given stimulus, so we're studying the processing of one stimulus in a noise-free display, we often use external noise, and when we do so, we actually assume that the noise that we're adding does not change the way the observer decides to process the information, or the way the observer is processing the information. And what we saw is that when we add local noise, so this is for pixel noise. When we have local noise, the processing strategy can change. So you cannot assume a priori that the processing strategy never changes just because you're adding noise or adding variance to your stimulus. Even though when you look at the model itself, it seems to be obvious that the processing strategy will never change just because you're adding noise. We just shown that this is actually not always the case. Same thing for a different paradigm here, voluntary averaging, where when you don't average samples that are quite different the same way that sample that appears to you as being all the same. So voluntary averaging, which is really a high-level task, you're not going to average samples if they all look the same to you, and it's actually no real way to actually consciously averaging these samples. So before finishing, I want to make an announcement. We have a special issue coming up exactly on this topic, so on the topic of using noise to characterize vision. And the deadline for abstract and full text submission is coming up, so we already have about 10 contributing authors. And if you're interested in participating to this, or if you have any questions, don't hesitate to contact me. Thank you.
Thank you, Rémy. Do we have any questions? I think that looks like Josh heading for a microphone.
Yeah, for those in the audience that everybody knows that Daniel sort of set this up as a point-counterpoint thing, and I'm going to talk about orientation averaging later, so I don't want to ask Rémy anything about that, but I was intrigued by your findings concerning detection and recognition, and I was wondering whether you gave any thought to how those two processes differ in the visual system.
What do you mean two processes differ?
So it seems like if there was crowding, you inferred that it was recognition.
Yeah.
If there was no crowding, you inferred that it was detection.
Yes.
But is that, can you be any, is that any deeper intuition than just renaming the result?
Renaming the result?
Yeah, so if you have crowding, I'm going to call it recognition. If you don't, I'm going to call it detection.
I'm not sure I get your, exactly the question.
So how does the process where you decide which side
okay. In this condition, I don't think you actually decide whether you use recognition or detection. What I think happens is that if you have two objects that appear, when you have the noise that appears, then your detection process actually operates, but you detect something on both sides. So you cannot use the detection process anymore because it detects something on both sides. Then you got to use another strategy. You have two objects, then you use a recognition task. So it's not a conscious decision of changing your strategy. It's really a consequence because the detection system just detects something in both conditions, so you cannot use detection anymore. Yes?
Rémy?
Do you think it's possible that there is actually one model that would account for both sets of results? For example, you could have a model where the pool, say the averaging paradigm, the averaging pool is determined by the similarity of the patches. So it's one model, just you have some gain control mixer that you can adjust, and it's adjusted by the stimulus, and that would capture all of it.
Well, Josh is going to present one of these models. So yes, there is possibilities to explain this within one model. And the thing is that, and there's other options. You can probably explain this within one model, but if you have a sort of a gate in your model, and you have two processing that occurs, then even though you explain this with one model, this still compromises the application of using the noise. When you're using the noise, you're assuming that it's exactly the same processes that are involved, and if you have a switch somewhere that depends on whether the gabors look like having the same orientation or not, then even though you can explain this with one model, this still compromises the application of the noise model. But what Josh is going to present is an alternative. She's going to try to argue that you can explain this with one model and being exactly the same processes being used when there's low variance and high variance, so don't miss this thought.
I have another option that might answer these two previous questions. Instead of calling it noise, instead of calling the external noise noise, what about calling it a mask?
Okay. Okay. Well, I don't really exactly get where you were going with this. If you call it a mask, yes, it's a mask, but I'm not sure what it actually changes.
Perhaps that will become clearer in Vincent's talk. One quick question from Michael.
Very quick, just a quick comment actually, and things may change, but it seems to me so far that what's being attacked as a standard model is a straw man. I mean, the standard models of detection and discrimination make ample provision for differences in strategy and indeed depend upon them. Consider off-frequency looking as a very simple example.
Okay, thank you. Well, I'm not sure that was just a comment, right? Okay.
Okay, I think we should move on to the next speaker. So, thank you very much, Rémy.